this class. Okay, Bixin has a question saying, you did all the homework? No, you can only do 8 homework, right? So we'll have more homework coming. So you only get 30%. If you get a 30%, that means you have finished 6 homework. Do you mean you finished 8 of them? I only received, so I think I updated grades for homework last night. If you send me today, it hasn't shown that yet. So if you get 30%, because each homework worth 5 points, that means you have finished, you have sent me 6. So the homework 1 is online. So 2 up to 8, right? That I assigned you. So that means you have sent me 5 homework plus the first one, 6 homework. All right. Bixin, does that answer your question? Raw. Oh, raw, I didn't receive all of them. I only received, for if you get 20%, that means I only received 3 of your homework plus the first one. Is it possible you send me, you resend me again? Okay, if you think, right, if you think I didn't give you right grades, try to resend everything in one email, okay? So I will update your grades.
Professor, hi, can you hear me?
Yes.
Yes, this is Damon. So I've been sending you my homework, but I just checked the grade book and I don't see anything documented in there. So
Damon, hold on a second. Let me check Damon. You sent to my email, right?
yes.
Oh, you have sent to me 5 homework plus the first one, right?
Well, 6 as of last night and 7 today. All 7 today.
Oh, okay. 7 I haven't graded yet.
But the others,
Yeah.
I don't see any grades for the others.
Oh, this 30% includes everything. Each homework 5 points.
And I don't see points for my homework submissions.
Oh, okay. Do you know how to search on a Blackboard? You see Grade Center?
Oh, it's a Blackboard. I'm looking at my OpenPath. Sorry.
Oh, okay. It's on Blackboard.
It's Blackboard. Okay, sorry.
It's okay. That's right, Bixin. Right. 30% means you have sent to me. You have sent me homework 2, 3, 4, 5, 6. All right. Some of you haven't sent to me everything yet, so you don't get 30%. And some of you sent to me up to 8, you get 40%.
And where would it be in Blackboard again? Actually, never mind. I see my
The
grades.
grades. You see your grades.
Okay.
Yours is probably different from mine. Mine is called a Grade Center.
Oh, 30%. Okay, I have 30%. Thank you.
You're welcome. All right. Any other questions? Yeah, Zenith, right, 30% is up to 6, homework 6. If you don't get 30%, actually, supposedly, right, so someone finished the 8 homework already, so that's 40%. So up to today, you could get 40%. So, right. Okay, any other questions? When is the midterm? That's on the calendar, right? If you go to my Open Math, you see the calendar shows you the midterm, which is March 17th. So use Blackboard, all right, and use. So this is one of the good things about COVID-19. So COVID-19 basically pushes people to use technology we have or technology available. Right? You see, online class, brings everybody a lot of convenience. We don't have to travel, right? So try to use Blackboard, try to use Open Math, and everything you need on either one. All right. Okay. Anybody has any other questions? All right. So today we're going to talk about improper integrals. Okay, so this will be the last section we're going to talk about in chapter 3. So chapter 3, we covered integration by parts, trigonometric integrals, part of it, trigonometric substitution, then partial fractions. So we're skipping 3.5, 3.6. So the last one we're going to talk about is today's improper integrals, right? Then we're going to skip chapter 4, introduction to differential equations. We're going for sequences and series, then power series, then chapter 7, parametric equations, and polar coordinates will be the last one. All right, so today we're going to finish chapter 3, improper integrals. So what do we mean by improper integrals? So we have to deal with the lower limit or upper limit to be infinity. So 4 will be part of the midterm, I'm assuming. What do you mean? I don't understand. What do you mean 4 will be part of the midterm? Oh, you mean chapter 4? Yes, it will be 1 week, Let's see if we have, so March 17. So March 17 is going to be our midterm, and which means March 15 will be review class. So whatever we finished by March 10th is going to be covered in midterm. All right. If up to now you still have no idea which day is midterm, you are really, really behind the schedule. March 17 is midterm. Please use, so you have registered for this class, right? So really take responsibility. Be responsible for yourself. You have registered for this class and you want to pass this class, right? So you are supposed to do what are you supposed to do? So midterm, I have posted the midterm date, a long while ago. If you still have no idea, I don't know where you're going. I don't know where are you going for this class. It's so difficult for me in the end of each semester, give a student F. I don't like to do that. I don't like to do that. But if you don't show any effort, right, you're not catching up with this course. So, what's the end result? How are you going to expect yourself to pass this course? And this course is not an easy one. It's not a very difficult one either, because I'm trying to, to just go through the basics. Your homework also, I'm trying to just cover the basics. So please take responsibility, be responsible for yourself, all right? So midterm, again, is March 17th. March 15th is going to be a review class, all right? Okay, so improper integrals means we don't have definite number for lower limit, for upper limit, and we have to deal with infinity, the idea of infinity. It could be negative infinity, it could be positive infinity, signs. Oh, you don't see my screen? Okay, James, you have to check your side, right? Paul, okay, reload, right, because I can't see it. All right, anybody has any other questions? All right, let's see some definitions. Let's see the definition of improper integrals. Okay. So I have two situations. The first one is let f of x be continuous, because the integrand always to be continuous in the interval. In the interval means the lower from the lower limit up to the upper limit. Right? It has to be continuous within the lower limit and upper limit. And in this case, lower limit is a, is a number, upper limit is positive infinity. Then this integration from a up to positive infinity for this continuous function in this interval equals to limit of t runs to positive infinity, where the integration from a to a dummy variable t, right? So t. Remember before we use n, right? We used this idea before. And so that's how we define if we have upper limit as positive infinity. Similarly, if we have lower limit as negative infinity, okay, provided this limit exists, okay, provided this limit exists, sometimes the limit may not exist. So second, the integrand still continues over the integral, over the interval, right, from negative infinity up to b. Then we define this as a dummy variable t runs to negative infinity from t up to b. So this definition is not strange, right? This is how we define integral sign before. So in each case, if the limit exists, then the improper integral is said to converge. Converge means, you know, the limit exists and it comes to a number, right? And the versus diverge. If the limit does not exist, then the improper integral is said to diverge, which means it does not reach a number. Right? So that's these two definitions. Okay. Well, three, the third situation could combine first two, where the lower limit is negative infinity, the upper limit is positive infinity. So the integrand is a continuous function over all real numbers. Right? Think about the integrand to be a polynomial functions. So we can split this into two. So the first one is from negative infinity up to 0, right? The origin of the real number line. Then the second one from 0 up to positive infinity. So we can always split two. Then we use the first definition and the second definition. And of course, provided the first part and the second part both converge, right? Which means the limit exists for the first one and the limit exists for the second one. Then we will reach a number. If either one or both of these two integrals diverge, means not converge, then this improper integral diverges. Okay, because we split it into two parts, you know, as long as one of it diverges, so this whole integral from negative infinity up to positive infinity diverges. All right, and this doesn't have to be 0, right? So when we split into two parts, it can be any number. So 0 can be substituted by any number. So we can write as from negative infinity up to a, and the second one from a up to positive infinity. Okay, so those are the definitions for improper integrals. So now, so before we're talking about definite integral, right? So definite integral, the lower limit is a number, the upper limit is a number. Then after calculation, after anti-differentiation, after substitution, then we get a number, definite integral. And the indefinite integral, after, you know, we don't have a lower limit, we don't have an upper limit. After integration, we add c to it. So we get a family of functions. So it really depends on c. And this third one is called improper integrals. So we're dealing with infinities. dealing with negative infinity and positive infinity. So this is called improper integrals. Let's see this example. Okay, so let's read this one. In our first example, we return to the question we posted at the start of this section. Is the area between the graph of f of x equals 1 over x and x-axis over the interval from 1 up to positive infinity finite or infinite? Let's see this one. So finding an area. Determine whether the area between the graph 1 over x and the x-axis over the integral 1 up to positive infinity is finite or infinite. Let me see if they have a picture of it. Yes. So from 1 up to positive infinity, and we know 1 over x graph, right, approaches to x-axis, approaches the x-axis when x goes to infinity. So this is the graph. Of course, this graph keeps going to the right. So we can see the area of this region is given by, well, we can set up this integration from 1 up to positive infinity, 1 over x dx. Then we can use the definition, take a limit, use the dummy variable t, let t run to infinity. Then the integration upper limit can be changed to t, so 1 over x dx. So anti-differentiate 1 over x, that's a natural log with absolute value of x, because we want to force, because the domain of natural log is positive number. It's positive number. Do we really have to do this? We don't really have to do this in this case, right? Because you see our integral runs from 1 up to positive infinity. So ln1 is 0, so we're fine. So take a limit, t run to infinity, ln of x, right? Then we evaluate x from 1 up to t. So that's the limit when t runs to infinity, ln of t, and minus ln of 1, right? Well, ln of 1 is 0, so we just have a limit when t runs to infinity, ln of t. Remember the ln x graph, starting from, right, it keeps going. So the range goes to positive infinity. So we get a positive infinity. So what does this mean? That means the area of this cannot be a finite number. It reaches to infinity. So we see this diverges. Okay, you see the integration, the limit diverges. Since the improper integral diverges to infinity, the area of the region is infinite. Okay, the area of the region is infinite. Right, so this is the first example of dealing with improper integrals. Anyone has any questions? All right, let's see more examples. So let's see. Does the integral diverging always mean the area is infinite? Yes, you could see that. Okay, let's see. We have these two words. One is called converge. One is called diverge. Okay, converge means it reaches a finite number. Okay, the number could be very big, but it reaches a finite number. So later on, when we talk about sequence and series, we're going to use this word again. We call, a series is convergent, or a series is divergent. Converge basically means, this integral reaches a number, a finite number, not infinite. Okay, it's a number, a real number. And diverges means, yes, it goes to infinity. It's not a number. It goes to infinity, means it diverges. Because infinity is just an idea, right? How big is infinity? No one cannot imagine. It's just an idea, a concept. So basically, it's not a number. That's it. So when it reaches a number, doesn't matter how big the number is, it converges. Or later on, we're going to call, the series convergent. Divergence means it doesn't reach a number. It goes to infinity, either positive infinity or negative infinity. Diverges. Let's see this example. Find the volume of the solid obtained by revolving the region bounded by the graph 1 over x and x-axis over the interval 1 to up to positive infinity about the x-axis. Let's see the picture first. So that's the picture, right? So from 1 up to infinity, this keeps going to the right, okay? To the right, so there should be an arrow in there. So this graph is not the whole thing, it's just part of it. Just imagine this is an infinite, like a cone shape. Cone shape, it keeps going to the right, keeps going to the right. So the solid is showing here using the disk method, right? Pi r squared. What's pi r? What's r? R is just a function value, right? It's a function value. So we have pi r squared. Pi r squared, r is the function value 1 over x. When we square, we get a 1 over x squared. Then we use the definition of for improper integrals, right? We change the integration to, we add a limit. We use a dummy variable t. The t runs to positive infinity. Then the upper limit, from positive infinity, we change to be t. Then 1 over x squared dx. So we anti-differentiate this 1 over x squared, we get a negative 1 over x. Right? Then we can evaluate it from 1 to t. When we do that, we get a pi, take a limit, when t runs to infinity, negative 1 over t plus 1. Well, when t runs to infinity, 1 over t is a very, very small number. So which means the limit of that is 0. And with the negative, it's also 0. So we just get a pi limit, t runs to infinity, 1. Well, what's the limit of a constant number? It's just a constant number itself. It's just 1. So pi times 1, we get a pi. Isn't this interesting? Is this interesting? Because we're trying to find the area. The area is infinite. Now, when we're trying to find a volume, the volume equals to pi, right? So the volume of the infinite cone converges to pi. So the volume of the solid of revolution is pi. It's just by calculation. This is not a proof, but you could see, right? You could see the contradiction right here. And if you are math major, you can think more about this. Yeah, pure mathematics, right? Pure mathematics is not intuitive at all, right? Sometimes it doesn't make sense at all. But by the calculation, because the definition has no problem, right? We have no problem with the definition. The definition, you cannot pick a hole here from the definition. The definition is perfect. Definition is great, right? We cannot say, oh, the definition is something doesn't work, doesn't make sense in the definition. So, but the definition makes sense. Then we use the definition, we use the prior knowledge to find all those. Find the area is, it's infinite. But now when we try to find a volume, yes, the volume equals to pi. Yeah. Right. Yeah, if you are going to major in mathematics, this is going to be one of the very interesting, question you can think about. If not, just don't worry about. Anyone has any questions? We just go through the calculation, right? We use the definition, we use the anti-differentiation techniques, then we reach the answer. In this case, it converges, it reaches a number pi. Yeah, so normally we just call this one infinite cone. Because this going to the right, infinitely. Yeah, you could think that way, yes. Because the pi is an irrational number. It never ends. No one knows the exact number. Yeah, pi is irrational number. Okay. Let's see this example. This example seems interesting. Traffic accidents in a city. So the question is saying, suppose that at a busy intersection, traffic accidents occur at an average rate of 1 every 3 months. After residents complained, changes were made to the traffic lights at the intersection. It has now been 8 months since the changes were made, and there have been no accidents. Was the change effective, or is the 8 months interval without an accident a result of chance? Probability theory tells us that if the average time between events is k, the probability that x, the time between events, is between a and b is given by this. So probability of it happens from a to b. It's the integration from a to b, a function dx, where a function is defined as this. It's 0 if x is less than 0. Well, of course, right? There's no accidents. Okay, if x is greater than or equal to 0, so if x is greater than or equal to 0, the function is k e raised by negative kx. What's k? K is the average time between events is k. So it's an exponential function. And it's exponential decay also. Thus, if accidents are occurring at a rate of 1 every 3 months, then the probability x, the time between accidents is between a and b, is given by this. Okay, because if it's 3 months, because k is the months in between. Right? If it's in 3 months, that would be 3e raised by negative 3x. So x greater than or equal to a for 8 months. 8 months or more than 8 months, just to anti-differentiate this. Right, then what do we get? So the probability for the months greater than a or equal to a is this. We use the definition, we anti-differentiate. So in the end, we get this. We get a 3.8. So very, very small number. Very, very small. So how do we interpret this? So this value represents the probability of no accidents in 8 months under the initial conditions. Since this value is very, very small, it's reasonable to conclude the changes were effective. Okay, so this is how we use in life applications. Any questions for this? This kind of question is not our focus, okay? Our focus for this course is basically to learn the integration skills. Let's see this one. Evaluating an improper integral over an infinite interval, right? So negative infinity up to 0. The integral is 1 over x squared plus 4. Right? This, remember, the x squared plus a squared. Anti-differentiation is arctangent. Okay, so we want to show whether the improper integral converges or diverges, right? If it reaches a number, that means it converges. If it doesn't reach a number, it goes to infinity or negative infinity, that means it diverges. So we use a definition, right? We use a variable, let's see, in this case, we want to use t. Okay, so this x is a typo, this is t, this x should be t. So typo here, t. So we use a dummy variable t, say let t run to negative infinity, then we substitute t as the lower limit for negative infinity. So 1 over x squared plus 4, that's x squared plus 2 squared. But anti-differentiate that, that's arctangent of 1 over a, which is 1 over 2, arctangent of x over 8, x over 2. Then we want to evaluate this from t to 0. So from 0, just get arctangent of 0. So limit arctangent of 0. 0 divided by 2 is still 0, right? So t is arctangent t over 2. Arctangent t over 2. Well, this we don't have the graph. You could think about the graph of arctangent, right? When t runs to negative infinity, remember the arctangent graph, those are U shapes, right? Should I let me just arctangent. Arctangent graph. Let's see this arctangent. Arctangent. When the variable approaches to infinity, when the value arctangent takes a value, takes a number, t over 2, it means infinity. It approaches to pi over 2. Right? So it approaches pi over 2. What about arctangent 0? Oh, actually, let me show you this graph. Right? See this graph. Arctangent 0 is just 0. Arctangent keeps going to the infinity, takes a value of infinity, it just approaches pi over 2. Right? So limit approaches pi over 2. So the first product gets 0, then we get pi, so 0 minus pi over 2, right? Pi over 2. But t is negative infinity, so get a negative pi over 2, the other branch on the other quadrant. Because t approaches negative infinity, so arctangent takes a negative infinity divided by 2 is negative infinity. Arctangent takes a negative infinity number, so that approaches to negative pi over 2. So 0 minus negative pi over 2 is 0 plus pi over 2. So half times pi over 2, that's pi over 4. Okay, so this one looks like a homework question. Homework question will be similar to this. Anyone has any questions? Okay, let's see this one. Evaluating this improper integrals from negative infinity up to positive infinity. Okay, so the domain of the integral runs all over real numbers. The integral is x e to the x. Now we need to use integration by parts, right? So we need to integration by parts. But we just split. We have to split this into 2 integrations. We split from negative infinity up to 0 and 0 to positive infinity. Then we use the definition. For the first part, negative infinity up to 0, we use the definition that t run to negative infinity. Then we use the integration by parts. So after do that, to get this, we get to take a limit, t runs to negative infinity, x e to the x, right? This is uv minus e to the x. Evaluate from t to 0. Evaluate from t to 0, what do we get? You get -1 minus t e to the t plus e to the t. Well, take a limit of this when t runs to infinity, what do we get? We get negative infinity. So -1, or here we have negative infinity times e to the infinity plus e to the infinity. So basically, we have negative, hold on, how do we get -1? So take a limit, t runs to infinity, t times e to the t. Oh, okay. E raised by negative infinity, what's that? E raised by negative infinity is exponential decay. Exponential decay goes to 0 very, very fast. You know, approaches to 0 very, very fast. And exponential function, exponential growth reaches positive infinity fast, but exponential decay reaches 0 very fast, much faster than infinity itself. So when we have t times e raised by negative infinity, so this also goes to 0. Because t is a linear function. T itself is a linear function, right? It grows with a constant rate, so it grows very slowly. But the e to the t decays, so the t is a negative infinity, it decays very fast. So it surpasses the linear function. That's why t times e to the t, when t runs to negative infinity, it also goes to 0. And of course, e raised by negative infinity, that's 1 over e raised by infinity, which means, you know, 1 divided by a huge number, which also goes to 0. So that's why this is just -1. This just equals -1. The textbook says, note, limit when t runs to negative infinity, t e to the t is indeterminate of the form 0 times infinity. Thus, we can use L'Hopital's rule. We can use L'Hopital's rule to write as t raised by e to the negative t. So this is one of the techniques, right? So t multiplied by e to the t, we can write as t times 1 over e to the negative t. Then we differentiate the numerator, we differentiate the denominator. So differentiate t, we get 1. Differentiate e to the negative t, we get negative 1 over e to the negative t. So take a limit of that, that's negative e to the positive t. Or e to the positive t is negative e raised by negative infinity, which is negative 1 over e to the infinity, which goes to 0. Well, so this you can do L'Hopital's rule, or sometimes you could just do by analysis, right? You can do by function analysis. So either way. Okay, anyone has any questions about this? All right, let's keep going. So the second part is from 0, lower limit 0, upper limit is positive infinity. We do the same thing, right? Integration by parts. So get this one, then, but now t runs to positive infinity. So that means e raised by positive infinity is again is indeterminate, right? You could write this one as indeterminate. But then when we take a limit of that, so t is, we can do by analysis. T is a huge number. So t minus 1 is a huge number. And e to the t is a huge number. A huge number multiplied by a huge number is a huge number. Plus 1 is a huge number. So this one we can do by analysis. You can do by analysis, function analysis. So this means that this limit goes to infinity. So that means the second part, the first part converges. The first part converges to -1. But the second part diverges. So if one part converges, the other part diverges, that means this whole thing, to answer this question, this means that from negative infinity up to positive infinity, it diverges also. All right. So as long as one part it diverges, the whole thing diverges. Okay, any questions? All right, let's keep moving. Okay, let's try this one, 3.27. Why did the evaluation of the antiderivative change? Why did the evaluation of the antiderivative change? What do you mean? Which part? Evaluation of the antiderivative. This one? Are you talking about this one? Evaluation of antiderivative. Oh, I see. Why did it change? What do you mean, why did it change? So anti-differentiate, we get this. T e to the t minus e to the t plus 1. Take a limit, let t run to infinity. So then, oh, you mean this line? What do you mean change? Which part change? Why do you evaluate? What do you mean change? Which part changes? Is the same integral? Yeah, the same integral, right? This is a integration by parts. Different evaluation on the next line.
Professor, can you hear me?
Yes.
So my question is, why is it the evaluation different? So if you scroll up a bit, you'll see that the third line is -1 plus t to the et. I mean plus,
You mean this one?
yes. Why is that
You mean
different
compared
than?
to this one? Okay, look at this. This lower limit is t, upper limit is 0.
So that
So they're
changes it.
opposite.
Okay.
Yeah.
Oh, okay. All right.
This one lower limit is 0, upper limit is t. So
Okay.
basically they're different by negative sign.
Okay. Thank you.
Right? You're welcome. But good eyes. Yeah, they are different by, right? Because when we switch the lower limit and the upper limit, that introduce a negative sign.
Thanks.
You're welcome. Okay, now everybody try this. 3.27. So I'm going to take a picture, take your attendance. Let me see. I think Masha, Eli. Let's see the homework. Alexander Borovsto. Alexander, let me see if Alexander is here. Oh, Alexander, you are here. Can you hear me? Right, I haven't received any of your homework yet. I haven't received any of your homework yet. Do you have any questions? Or is it too busy? No time to do your homework? Oh, okay. So you sent to Brooklyn one, all right? I typed it in the type in the chat my Brooklyn College email address. Let me see whom else. So Paul already have an answer. Okay, let's see whom else. Sure, I don't think I ever seen him in a class. Not sure. Right, no, but some people may be withdrawn already. Let's see who's next one. Damani, I don't think. Damani, nope, not in the class. Damani. Jack is in the class. Okay, some of you already got E to the 3. Jack, I haven't received your homework, any of your homework yet. Nuzet, N-U-Z-H, Nuzet. I'm sorry, I don't know how to say your name right. Okay, good job, guys. I agree with you, yeah. Nuzet. No, okay, I don't see him. Michael, I never seen this guy in the class. Okay, anyway. So we all get E to the 3. Anyone did not? So we just use the definition, right? We use the definition. We use the dummy variable t. Okay. We use the definition. We use the dummy variable t. We said, okay, let t, so take a limit, let t run to positive infinity. Then we change the upper limit to be t. So the lower limit is -3 runs to t, e to the negative x. Anti-differentiate, we get negative e to the negative x. Right? Then we evaluate e to the negative x from -3 up to t. What do we get? Well, e to the negative x, if we change it to be e to the negative infinity, that goes to 0, right, when we take a limit. So only left with e raised by -3. Well, -3 becomes e to the 3. Yeah, I agree with you guys. It is e to the 3. Anyone has any questions? Can you show the work on the whiteboard? Oh, sure. We just use the definition, right? So question is, the lower limit is -3. The upper limit is positive infinity. And the integrand is e to the negative x dx. Okay, what do? We use the definition. Let me change my color. So you want to use the definition, limit. Then you use a dummy variable t runs to infinity. Now, because we let t run to infinity, we use the limit idea. We change this upper limit to be t. Right? So the upper limit becomes t now. Now we anti-differentiate. When we anti-differentiate, we get negative e to the negative x. Right? Then we evaluate from -3 up to t. Of course, we still carry the limit with us. Limit t runs to infinity. Right? Well, anti-differentiate t infinity, right? So e to the negative infinity, of course, is 0. Right? get 0. All right, I'm not going to write it. So negative, so the first part will get negative e raised by negative infinity. E raised by negative infinity means 1 over e to the infinity. Right, so 1 over a huge number, when we take limit, that puts us to 0. So first part will get 0, then 0 minus negative e to the negative 3. Well, negative 3 means plus 3, right? Minus minus becomes plus. So we just get e raised by 3. That's it. Does this make sense? Right, Jeff? Okay. All right. Let's keep going. Okay, integrating a discontinuous integrand. So in mathematics, we call something called removable continuity. Just imagine, imagine we have a rational function. Imagine we have a rational function. And this rational function somehow can be simplified to be a polynomial function. Right? Let me just give an example. Let me just type in the chat. Think about f of x equals to, the numerator is x squared minus 4 divided by, the denominator is x minus 2. Let's do x plus 2. X plus 2. So this one we can simplify, right? Because x squared minus 4 is difference of two squares, can be factored as x plus 2 times x minus 2. So this can be simplified as x minus 2. Right? But the first one is rational. The first one is a rational function. So the second one is a linear function. So if we graph the first one, so I type the f of x in here. So the second one is simplified after simplification. So first one, positive 2 and negative 2 is not in the domain. Just remember, when we graph it, we still graph a line for f of x equal to x minus 2, but at x equal to negative 2, we will make an open circle, right? Because negative 2 is not in the domain, and f of negative 2 is not in the range. So we'll make an open circle to indicate that. And when we take, if the integrand is somehow like this, like f of x, right? We have this, because negative 2 is not in the domain, so the function discontinues at negative 2. So what do we do with that? So this is integrating a discontinuous integrand. So let's see this graph. So let's see in this case. So we want to integrate from a to b f of x dx. And somehow we're integrating over, and the integrand is continuous over from a to b, but including a, not including b. Okay, so b itself is not really the upper limit, but a number close to b is the real upper limit. And the function discontinues, especially discontinuous at b. Right, so b cannot be the upper limit. So what do? We're going to take a limit. Okay, we'll take a limit, let t goes to b, approaches b, but a little smaller than b, right? Because this integral is from a to b, from a to b. So because not including b, so all the values in the interval from a to b are smaller than b, so less than b. So that's why we write t approaches b from the left. From left means, t is a number smaller than b. Then we use the dummy variable t to substitute the upper limit b. Upper limit b. So think about the function, the example I give to you, right? f of x equals x squared minus 4 divided by x plus 2. So we could just stop integration from there. So b is not in the domain, no problem. I can use this definition. Take a limit, let t runs to a number less than b, which is indicated by b raised by negative sign. Then the integration from a to t. So this t is a dummy variable. Then because of this, so we can anti-differentiate, right? Then evaluate at a at t, then take a limit of it. So the idea is still same as before. Let's see an example. Of course, we have two cases, right? One case, interval a and b, from a to b, and a is in the domain, but b is not. Or at a is continuous, but at b is not. Or from a to b, the lower one, the lower limit is not in the domain, or the lower limit is not continuous, but the upper limit is. So I have these two cases, right? For the top case, from a to b, but b is not in the domain, or the function discontinuous as b, so we take a limit, let t run into a number less than b, which is b raised by minus sign. If the lower limit a is not in the domain or discontinuous at a, so we would say let t be a number a little bigger than a, right? Because a is the lower limit. So let a number be bigger than a. So we write as t approaches to a raised by plus, a raised by plus sign. Then integration, we change the lower limit to be t. Okay, so let's see some examples. And of course, of course, if from a to b, we do have some discontinuity at a certain point. Let's see, in this case, c. So we can break up this interval from a to b into two intervals, right? From a to c, from c to b, then we use the limit idea. Well, if we have a couple more, we will break a couple more, right? We will, break this interval into a couple more intervals, then integrals, then use the idea of a limit. So as long as one of it diverges, then the whole thing diverges, right? Let's see an example. So this integrand, so the lower limit is 0, upper limit is 4. This integrand is 1 over square root of 4 minus x. Can x be 4? No. 4 minus 4 is 0. We get a 1 over 0. So 4 is not in the domain of this function. Right? So 4 is not in the domain of this integrand. So what do we do? So all this is whether the integral converges or diverges. Okay, we use the limit idea. We rewrite this one. We use dummy variable t. We say let t be a number less than 4. So then we change the upper limit 4 to be t. So we anti-differentiate this. After we anti-differentiate, we get this negative 2 square root of 4 minus x. We evaluate from 0 to t. Evaluate at the t, so we get square root of 4 minus t multiplied by negative 2. And plus this, so 4 minus 0, which is square root of 4, which is 2. 2 minus the negative 2, which is negative 4, minus the negative 4, which is plus 4. Right? Now, t is a number smaller than 4. T is a number smaller than 4. Right? Think about, so t is very, very close to 4. But in this case, we could just substitute as 4. Right? So 4 minus 4 is 0. 0 times -2, just get 0. So we get 4. So limit of 4, which is just 4. So this part, so yes, so this one, it converges, because it converges to a number. Because the integration will get a number 4. Okay, any questions? Where does the 4 comes from again? Oh, the 4 is given in the very beginning. Let's go to the question itself. Okay, you see the integration is from 0 to 4. The lower limit is 0, upper limit is 4. But however, 4 is not in the domain of the integrand. That's the problem. Does it make sense? Okay. Okay. So this technique is when we deal with function discontinuous at a certain intervals. So we can remove the discontinuity by split the integration into different intervals. Then use the limit idea. Take the limit. Then use the dummy variable. Okay, let's see this one. So this is 0 to 2, right? X, ln x. Ln cannot take 0, right, as a value. What's ln 0? Not defined, right? The domain of ln is positive number, greater than 0. So what do? We use the idea of limit. But this part is the lower one, right? The lower limit is not in the domain, so 0 is not in the domain. So we use the limit idea, right? We use the dummy variable t, right? We say t is a number a little bit bigger than 0. So then the integration lower limit becomes t runs to 2. Then we'll anti-differentiate, right? We anti-differentiate by parts, integration by parts. So get this. Then we evaluate at t at 2. So then we get this. We get a quadratic function in terms of t. Right? So when t approaches 0, the t term becomes 0 term. So we're left with 2 ln to minus 1. So limit of 2 ln to minus 1 just itself. Okay. How do we know which interval is not included again? You mean which one is not in the domain? All right, so that means, okay, that means we have to know functions very well, right? Polynomial functions are very easy. Polynomial functions run through all real numbers. So usually, so let me give you a list of this. Actually, let's go to the whiteboard. Let's review some functions. So rational functions. So first branch is rational functions. Okay, let me tap first. Polynomial function we don't have to worry about, right? We use power rule for anti-differentiation, and the domain is every real number for polynomial functions, so no worry. The worry starts with rational functions, right? Rational functions, first one, square root functions, square root function, and what else? Square root or even, or any even real functions. Right, log functions. Right. Logarithmic functions. What else? Sine, cosine takes everything, right? So let's just go through these ones. Oh, you got it. Okay, right. Just as long as, you know, it's okay. Not to worry, not to worry, right? So we're okay with this, right? Everyone okay with all those functions, right? We should know functions are really well by now. All right, so let's go back to the textbook. So in this case, ln x, 0 is a problem for ln x, right? If you remember the graph of ln x, right, the value of x cannot be 0. It can be very, very close to 0, but will never be 0 itself. All right, let's see. Okay, let's see this one, integrating this one. So what happens from -1 to 1? So the value 0 is not in the domain of this integral. So we have to split into two, from -1 to 0, then from 0 to 1, then use the limit idea. So split from -1 to 0 and 0 to 1, then the rest should be easy, right? We use the limit idea, let t run to 0, very, very close to 0. Then we anti-differentiate. Oh, this one gets to positive or negative infinity, which means it diverges, right? As long as one of it diverges, we don't even have to evaluate the other part anymore. So the whole thing diverges because it reaches positive or negative infinity. Anyone has any questions? All right, let's keep going. You try this one. You try 3.28. So the integral is 1 over x, or 0 is not in the domain. ln2 plus infinity, so it diverges. Right. Right. If the answer with infinity diverges. Anyone has any questions with this? All right. Okay. A comparison theorem. Okay, yeah, it diverges. Thank you. Okay, so we all agree it diverges. So sometimes maybe it's not easy to find if the integral diverges or converges. We can compare. We can use this comparison theorem. So let's say we have two integrations. So the integrand, one is f, the other one is g. And they're living in the same interval from a to t, Just the integrand is different. And if those two so if let's see, if f is bounded in between 0 and the g with the integrand g, like this, right? You see f, the area under f from a to t, is less than the area under g from a to t. So if we know something, if we know g diverges, because g is bigger, so that means the smaller one diverges. Or if f converges, and we can see, no, if g converges, we could see the smaller one converges. If f diverges, so the smaller one diverges, so the bigger one diverges also. So that's a comparison theorem. Okay, so let's see the theorem itself. So we have f and g continues over a to positive infinity, and assume f is, f is in between of 0 and g. So we want both above x-axis, and the x value is greater than or equal to a. So the first part, if the integration from a to positive infinity of f, right, goes to infinity, so which means this f diverges, right? Then g also diverges. So the picture is this. Picture is this. So if f is the smaller one, right? Imagine the area, they didn't share the area from a to t. So if the area from a to t diverges, does not reach a finite number, if the smaller one diverges, the bigger one, so g, must diverge. The area under g from a to t must diverge also. Well, the other side is if the area under g from a to t converges, if the bigger one converges, so the smaller one must converges, right? The area under f from a to t must converges. But with algebraic expression, that's this. Okay, if the integral with the f diverges, then the big one, g, also diverges. If g converges, right, equals to L is a number, so which means it converges. Right? If the bigger one converges, the smaller one must converge as well. Okay, so this is a comparison theorem. Any questions? Okay, let's see how do we use this. So the integration from 1 to up positive infinity, the integral is 1 over x e to the x, right? 1 over x e to the x. X is a number in the interval from 1 to positive infinity. So we can imagine this denominator is bigger than 1 over e to the x, right? So this function, so this is f, and then we can imagine g is 1 over e to the x, right? So the integral 1 over x times e to the x is less than or equal to 1 to the e to the x. So if the bigger one converges, the smaller one must converge also. So we just have to show the bigger one converges. We just have to show the integration from 1 to positive infinity e to the negative x converges. So we show that, okay, from 1 to positive infinity e to the negative x, we read it for the definition, improper integral definition. Take the limit. Let the dummy variable t run to positive infinity. Then change the upper limit to be t. We anti-differentiate e to the negative x, get negative e to the negative x, evaluate at 1 and at t. In the end, you get e to the negative 1, right? 1 over e. So that's a bigger function converges. That means the smaller one, 1 over x e to the x, converges also. So this is by comparison exam theorem. Okay. Anyone has any questions? All right. Let's see this one. So 1 up to positive infinity, 1 over x raised by p. P is less than 1. To show, we want to show this one diverges. So we want to show this one diverges. So then what do we want to do? Yeah. If the smaller one diverges, the big one must diverge also. Right? Probably we want to find a function we want to find the smaller one diverges, so the big one diverges, right? I'm sorry, I have an allergy here. So for p less than 1, 1 over x less than or equal to 1 over x raised by p over the integral from 1 up to infinity. So we want to show 1 over x, right? So p equals to 1. Diverges. So we want to show a 1 over x diverges. Then, so if this diverges, if this is a big function, if this is smaller one diverges, so the bigger one must diverge, right? So 1 over x, think about it, is bigger than 1 over x. It's smaller than 1 over square root of x, right? X raised by half. Because p, we want p less than 1. P may be half, maybe 1/3, maybe 1/5, so on and so forth. So 1 over x. So you're always given the larger integrand and must choose a random smaller integrand. Well, it depends. Depends on which one you want to prove. Depends on which one you want to prove. Let's go back to the picture. Okay. So we have f and g. We have these two functions. Let's see we have f. Okay. Let's see now, first situation. Let's see we have f. We have f. We want to show if f. So we're thinking, okay, you know, by a good guess, by approximating, maybe f converges. But however, it's so difficult to verify f converges. But some integrand is not easy to integrate. So what do? We can find a big function, an easier function, which is bigger than this. You see this g, right? Every g at every point from a to t, g is bigger than f. So then g is an easy function. If we prove g converges, if the bigger one converges, if the bigger one reach a number, the smaller one must reach a number too, right? So this is one way of thinking. Another way of thinking, okay, we have g, we have function g. we're thinking, okay, I think this function diverges. Okay, I think this function diverges. But however, it's so difficult to prove it diverges. So what I'm going to do, I'm going to find a function smaller than that. I'm going to find a function f. If I can prove f diverges in the same integral, because this one is bigger than the smaller one, is bigger, if the smaller one reaches infinity, the big one must have to reach infinity also, right? Does that make sense? Okay. Okay, makes sense? All right. So basically, if you want to show it diverges, we want to find a bigger function. If we want to show it converges, we want to find a smaller function. So it depends. Okay, so we have two situations. It depends. All right, good. Okay, let's see. Did we finish? Okay, we finished this one. Now you try this one. You try 3.29. From e up to positive infinity, ln x over x. Okay. You want to show this one diverges, right? You want to find a smaller function. It diverges. You know, if the smaller one reaches infinity, this one is bigger than the other one, it must reach infinity also. Okay, I'm going to get a tissue. I'm having allergy here. Would the smaller one be 1 over x? 1 over x. You want to try 1 over x? From e to infinity. From e to, okay, you want to show it diverges, right? You want to show it diverges. You want to find a smaller function diverges. And this one is bigger than the smaller one, so this must diverge. 1 over x diverges from the previous example. from e to positive infinity. 1 over x diverges we did from 1 to positive infinity, right? So you could show that. Yeah. Yeah, that's not only one way. There are many ways. You can find many functions. Yeah, you can use it. Right? You can try that. I was thinking something else. From 0 to infinity. It'll be similar from e to infinity because e equals 2.71a, right? E is a constant number. It would be similar. I think you can use that too. Yeah, that may be easy one, I think. Okay. So this one, let me write this down. So this one is from e to infinity ln x over x dx. So we want to show this diverges. Okay, right, we want to show it diverges. But permissible, so which function you choose to compare? To compare with this integral ln x over x. Maybe let's all try together. Let's try the suggestions 1 over x. So let's see. We have from e to infinity ln x over x dx. So we want to show this diverges, which means it reaches a positive or negative number, positive or negative infinity, right? ln 2x over 2 plus c. Okay, the many so let's see, let's think. All right, we want to show this diverges. Let's make a picture of here. So let's say e is here up to infinity, right? It just keeps going. And let's call this f of x. Actually, let me see. Okay, the graph one. So if this is a 1, so 1 I got 0. So let's say 1 is somewhere here. So the graph goes this way, just keeps going down, keeps going, right? So from e up to infinity, of course, it diverges, right? This keeps going to the right. So it goes to infinity. So this is our f. And we want to show this diverges. So how do we do that? We are going to find a function, the area is less than this. is less than this. So from E up to here. So the function may be, I'm just draw anyone, all right? So let's say this is G. So we need to find such function G, and from E to infinity at every point, G, at every point, the function value of G is less than F. So just think about a graph like this. So the area here, right, is less than the area under F. So if we can show such G diverges, if such G is smaller than F diverges, then the big one must diverge also. So that's our goal. So we had a suggestion. The suggestion is saying let the smaller one be 1 over x. Right? E to the infinity. And we know that curve is at 1 equals 1, 2 equals the half, so on and so forth, right? Gotta graph something like this. Well, right? If we can show this one diverges from E to infinity, then we're done. So what do? We take a limit. We use dummy variable t, run to positive infinity, and then we change, let me change the color, change green, change the upper ground to be t. We anti-differentiate. When we anti-differentiate 1 over x, we got ln x, because I don't need to put absolute value around x because my lower limit is e, 2.7, right? So that makes sure, so that means my x in the interval e to positive infinity, so my x is positive. So I don't need to indicate, enforce it with absolute value sign. Then of course I'm gonna take a limit, t run to infinity, ln x. I'm going to evaluate from e up to positive infinity. All right, so when I do this, ln x, well, when x runs to infinity, what's that? Infinity, right? That's it. And then minus ln e, which is 1. Well, infinity minus 1 is infinity. So that's it. That's it. So this integrand at every point from e to infinity, this function is 1 over x. So when we write this proof, we have to write this way. Less than or equal to ln x over x greater than or equal to 0. Because when we use a comparison, we have to use this condition, right? And also x is in the interval from e to infinity. So this is true, this statement is true, right? So this statement is true for all x in the interval. So once this condition, so this is a condition, right? So then when we prove this one, the smaller one diverges, the bigger one must diverge. If the smaller one doesn't reach a finite number, of course the big one doesn't reach a finite number, right? If the smaller one goes to infinity, the big one, of course, goes to infinity. So that's an idea. Any questions? Okay, let's keep going. You may find other function works also, of course, right? There won't be one function work for this. The infinite many functions, smaller than f at every point from e to infinity. So there are many of them. All right, let's go back to our textbook. Have another suggestion for a function? Well, you could do so many, right? Think about the function that from e to infinity. think about, well, for this one, 1 over x is a good choice. There's so many of them. Use x. You mean use a straight line? X won't be, right? So ln x, you have to, you can find, because I was thinking, okay, you could use the meanings of them. 1 over x squared to the third, to the fourth, to the fifth, any power. This is one type of it. You may find others, right? Other type of it. All right. Let's go back. Okay, so this one diverges and Laplace transforms. Okay, I'm going to skip this. I think we're done with this section, right? So I'm going to assign you some homework from this one. So that would be homework 9. Right. Okay, so improper integrals. So we're dealing with infinity, one of the limits to be infinity or both of the limits to be infinity. We use the limit idea, or the lower limit or upper limit is not in the domain of the integral. So we use the limit idea, then we use the dummy variable. So that's it, that's for improper integrals. So overall, anyone has any questions? So you just send me your homework? Some of you just send me your homework. Let me see. But I haven't checked today yet. I haven't updated for today yet. Oh, okay. Let me see. I received. I received Rajab's 6 and 7. Reli 1 7. Zacharias 7. And Damon 7. Ali 7. James 7. And Ross, well, which one is this? Oh, homework 1 to 7. Let me see. Oh, you basically share your folder with me. Can I open it? Oh, yes, I did. Great. Oh, that's a great idea. Yeah, if you save your homework on a drive, on Google Drive, then you share your link with me. That would be much easier. You don't really have to send me each homework to my email anymore. That's a great idea. Let's see. Did I miss anyone? You can open. Yes, Raw. I just opened them. I just have opened all of them. I see all of them. Great, that's a good idea. Let me see anything else. Right, I personally use Google Drive all the time. I use it to store a lot of stuff. All right, great. Okay, anyone has any questions? All right, good night then. Have a good night, and yeah, see you on Thursday.
Professor?
Happy Women's Day. All right, thank you. Yes.
Have you gotten anything from me? I just want to check.